I'm going to show the problem of the day that I created for yesterday, June 22nd. This problem of the day has two parts. The first part's relatively straightforward, about linear and angular speed, and then the second part's pretty hard. It requires some thinking about modeling and problem solving, and I'll show you how you can sort of use GeoGebra software to model this, and then come up with the equations, confirm that they're right, and then use some calculus to actually solve the problem. So first of all, part one, Mr. Mill's riding a giant bicycle, tires that are 4 meters in diameter, very big. Riding this bike, I covered 12 pi meters in 3 seconds, find the angular speed. So it's relatively easy. We have our giant tire with 4 meters of diameter, meaning a radius of 2 meters. And in 3 seconds, we will cover 12 pi meters of distance. That means in 1 second, we will cover 4 pi meters per 1 second. Okay, since the wheel is rolling, we are wrapping the circumference. So I would want to know the circumference. Given that the circumference is 2 times pi times the radius, the circumference is 4 pi. So if I'm going 4 pi meters in 1 second, that is 1 circumference per second. So that means I'm doing 1 revolution per 1 second. So 1 rev per 1 second, or it might be helpful to think about it in radians as 2 pi radians per second. So this is my answer to number 1. Not too bad. Second one, a ladybug lands on a spoke of the wheel of Mr. Miller's bicycle such that it is 1 meter from the center of the wheel. While clinging to the wheel spoke, what is the total distance the ladybug travels in 3 seconds? So the ladybug's going to land somewhere on the spoke. It could be anywhere theoretically on this circle that is a radius of 1 meter, but let's just say it's right here. Or actually, for my model, I'm going to put it here. So let's say the ladybug lands 1 meter right here. Here's my little ladybug. Tough looking bug. Let's add some color to that thing. Yeah, there we go. So the ladybug lands on the spoke and it's going to follow some sort of motion, and then my wheel is going to end 12 meters later, somewhere around here. And the ladybug, because I've completed 3 full revolutions, and because this is 3 seconds, the ladybug's going to return to the position that it's in. We're going to try to draw them again. Okay. And we'll draw this, and we'll draw the little wings. Yeah, ladybug. Okay, so the question is, what's the distance the ladybug covered? And not the displacement, because the displacement's easy. It's just 12 pi meters of displacement. But the path the ladybug takes is actually going to be this interesting curve type path, because the wheel is spinning and moving. And so I want to model this situation. So I'm going to go over and I'm going to try to model this on the computer, on GeoGebra. And then we'll come back here and do our math once we have a good model created. Alrighty, now that we're on the computer, I'm going to hop onto GeoGebra, geogebra.org/geometry. I'm going to turn on my axes and my grid, and I'm going to build a model of this situation. So we said I have a giant bicycle, tires are 4 meters in diameter. That means the center of the tire I can think of as being some point A, and for the moment I'm going to put A at 0, 2. That would be the center of my tire. We said the radius would be 2 meters, so I'm going to build a circle around point A with a radius of 2. Awesome. Now I'm going to need this circle to actually move, though. So the way you can do that is you can build a slider. So if I type S equals, and I think S equals slider, there we go. And I can tell it the minimum value I want the slider to have and the max. So we're going to start the slider at 0. And we said that the bike did 3 full revolutions, which is 6 pi radians. So I'm going to say 6 pi radians is going to cover all the revolutions I need, and there's my slider. Now I am going to redefine point A, and instead of 0 as my x-coordinate, I'm going to use slider S. Okay, so now if I push play, off my circle goes. It's moving by S, which we defined as theoretically being rotations, and we did 6 pi radians for 3 rotations. But you'll notice we only get to about 19 meters. But we're supposed to get to 12 pi meters. And the reason is because I have 3 full rotations, but I haven't accounted for that my radius is 2. So I'm going to multiply 2 times s, and that's actually going to take my wheel the full path. So now I'll go all the way to 12 pi meters. And we're off, and let me just write the line x equals 12 pi, so you can see the circle should make it there. Brilliant. Okay, so that's very nice, and let's get that out of here. Scoot this on back. So now I've got my circle, which is good. Next, I'm going to have a ladybug. We said the ladybug landed such that it was 1 meter from the center of the circle. So I'm going to draw a new circle. Let's call it circle, well, we'll see what it calls it. Circle, and I'm going to say centered at point A with a radius of 1 meter. And that's where my ladybug is going to land, somewhere on that circle. Additionally, that ladybug is going to be rotating around in space. So I'm going to go to my tools, I'm going to click plot a point, and I'm going to put it on this circle, which GeoGebra is going to lock that point B. It's going to say B is point on circle D. So now if I drag B around, it stays on D. But to animate B, I can use a rotate tool because this wheel is supposed to be rotating. And so I want that ladybug to rotate as we move. So I'm going to use rotate object angle point. I'm going to rotate B, the ladybug, by the angle, I'm going to do -s because I want my rotation to look like a wheel turning, so I need it to go clockwise, which is sort of negative to the theta we've defined, and it needs to rotate about point A. So pressing play on all of this, there it goes. I can even slow it down a little bit, bring it back, and okay, this is my ladybug. Let's make it a little bit bigger to keep track of. Let's make it red. Great. Then I don't really need that B point. That was just built in, so I'm going to hide that object. Don't know why C is labeled. Okay, so if I press play again, there goes my ladybug, and there goes my wheel, and we're rotating through space and time. And what's really nice about this is that I can click on this point B prime, and I can click these 3 dots and click show trace, and now it's going to trace out the path that B prime goes in, or the ladybug goes in. So as the wheel is rotating and moving horizontally through space, we are carving out, and let's go backwards, we are carving out sort of this, I don't know, kind of looks like a sinusoidal curve of some sort. Cycloid maybe? I don't know. Something like that. But we can see we've got this path of motion. And this is useful because as I want to build an equation for the ladybug to try to calculate the distance of, I'm going to be able to check it against this curve because I've effectively modeled the motion. Now I'm confident I've modeled the motion. Now I want to try to build an equation. And so to build this equation, I'm going to think parametrically, and I'm going to define some point. Let's call it L for ladybug. And let's just say that L is given by, let's start with 0, 0 for a second. Okay, and there's my ladybug. Obviously, that's not where it is. If I think about what's happening on the wheel with the ladybug, one part of it is that the wheel is just moving horizontally. And it's moving horizontally at a rate of 2 times s. So I'm going to put 2s for point L, and then point L is going to scoot along with the wheel. I can also put plus cosine of -s, which is the same thing as cosine s, but cosine -s, because in theory we're rotating clockwise, I'm accounting now for the rotation of the wheel in my x position. And let's see if I can put it on B. So B is sitting at 2 at the moment. So there we go. We're on B. Now let's push play. And L now, if we look at it, seems to follow the correct x position. We haven't accounted for the y. I haven't touched the y coordinate yet. Let's slow this down. Okay, but L is following the Ladybug's x position. So I've modeled the x position by handling the linear component of its velocity and the rotational component of the x, of the x, the change in x. So now I just need to do the y. So for y, we're starting up at 2. That's where the Ladybug landed, we're pretending. And then the y is just going to be given by sine of x, or sine of theta. But I want it to rotate backwards so I could do sine of negative s, because s is our theta. And then now everything should work out. Ladybug follows the path of b prime, Ladybug L. So I'm confident now that my equation models this. So even though it might not look, at this point I've defined is a parametric equation. And so using this, I'm going to be able to go back and actually do out all the math now and solve for the length of this red curve. And I'm probably going to cheat and use Wolfram to do some of the calculus for me, but that's okay. Right, and here we go, b prime, same as L, and we're tracing this path. It's pretty cool. Scoot that on back, and here we go. So there's the path of the Ladybug through space as the wheel is theoretically rotating and translating horizontally. Very neat. And now it's bouncing backwards. I can also set this slider to only increase. So now when it gets to the end, it'll just restart. I can zoom up the speed here, and off it goes. Pretty cool. All right, so let's take it back to the math. Okay, coming back to this second problem, we've been able to model the path of Ladybug using GeoGebra, and we also were able to sort of visualize, I mean, it's not quite a sine curve, but it looks a little something like that. And we said we were able to get this little parametric, which we tested using a point defined as the following. We had 2s, and I'm going to replace s now with theta, plus cosine of negative theta, and then 2 plus sine of negative theta. So that was the equation that modeled the path of the Ladybug. So the next thing we're going to do is we're going to rewrite that as a parametric equation. So I'm going to say that the Ladybug's x position, x of t, position over time in the x direction, is given by, now, I guess it's not so much x of t as it is x of theta. So I'm going to replace theta with t, mixing and matching all over the place. So we'll do 2 times t plus cosine of negative t. At some point, I'm just going to switch that to cosine t because they're equivalent, but we'll roll with it for now. And then we're going to say our y-coordinate of t is equal to 2 plus sine of negative t. And so that's our parametric equation. This models the position of the Ladybug. L of t maybe could be composed of this parametric. I don't know. So if I want to find the distance covered, it turns out there is this formula for the distance of a parametric curve. So if I integrate the curve from a to b, and I sort of use this like distance formula thing, and so I take x prime t squared, kind of looks like Pythag, plus y prime t squared dt. And so basically if I take that integral over the interval a to b, I'm going to get the length of the curve, which is pretty darn neat. But that's going to require that I have x prime t and y prime t. So, I mean, I'm going to go hop on Wolfram. Not that these are particularly difficult derivatives, but not that current in calc. I'll try to do them, but I'll definitely check them. So we have x prime of t. Derivative of 2t is just 2. Derivative of cosine of negative t should just be negative sine of t. So I should just get 2 minus sine t. Let me momentarily check that just to be safe. 2t plus cosine negative t. 2t plus cosine negative t. 2t plus cosine t. Oh, forgot to type the word derivative. Yeah, okay, that checks out. And we want the derivative of y prime, so the derivative is 2, 0. Derivative of sine of negative t, well, that's the same thing as negative sine t. Derivative of sine is cosine, so I'm guessing y prime t should be negative cosine t. Let's just confirm that before we proceed and make a fool of ourselves. Plus sine of... Delightful. All right, the derivatives check out. And so if I have my derivatives, you'll note here I'm squaring the derivatives because we're taking sort of like change in x, change in y, and square rooting it. It's the whole distance formula idea. So let me square these things. So x prime t squared is going to be equal to 4 minus 2 sine t plus sine squared t. Great. Y prime of t squared is going to be equal to just cosine squared t. That's delightful, because if we put these all under our integral symbol, integrand, it's been a while, we'll end up with 4 minus 2 sine t plus sine squared t plus cosine squared t dt. But sine squared t plus cosine squared t, it's a Pythag identity, is just 1. So I'm going to end up with the square root of 5 minus 2 sine t dt. And I want the integral from a to b. All right, so it's about time we figure out what a to b ought to be. As far as the path of the Ladybug goes, we said we did 3 turns or 3 revolutions of our wheel. So we did 6 pi rotations of motion. Our function is built off of that. So that's what we're going to do. We're going to integrate this from 0 to 6 pi, and then be happy. Now, I don't see anything obvious about how to do this integral. Maybe it's not that hard. Maybe it is. Kind of beats me. But I'm going to go ahead and pop that into Wolfram Alpha, and let's see what we get. If you know how to do it, good on you. But I do not. So we're going to go from 0 to 6 pi, square root of 5 minus 2 sine t dt. And when we put that in, off it goes. It's calculating. Yeah, that doesn't look like it's particularly feasible to calculate. So anywho, we get that the path of the Ladybug is approximately equal to a distance of 41.7 meters. I mean, that sounds about right. If we do 12 pi, the 12 pi is 37.7 meters. The Ladybug's adding in some extra distance here. It seems like it could be accurate. The only thing I'm slightly concerned, everything looks okay. The thing I'm concerned about is this interval, the 0 to 6 pi. But I think we built the function so that that works. Yeah, so I guess that's what it is. We added another 4 meters through the rotation. Cool. So hopefully this was informative. hopefully my answer is right. You can try it and see if all this logic checks out, and if it's not right, please let me know. But I'm pretty sure the idea behind it is correct. It's nice to get a second opinion. So thanks for watching. Hope you enjoyed and found it useful and informative.